So welcome everybody to the One World IAMP Mathematical Physics seminar. Our speaker today is Cole Sanders from the University of Hanover, and he will talk about the entanglement and separable states in relativistic quantum field theory. Please go ahead.
Yes, thank you very much, Wojciech. I assume you will all be able to hear me and to see my slides, and otherwise, please let me know. So thank you, first of all, for allowing me to give a talk in this very nice online seminar series. The topic of my talk is entanglement and separable states, so states which are not entangled, and especially in relativistic quantum field theory. So what I will do is I will give a bit of a physical motivation why we should be interested in this, particular in the quantum field theory setting. Then I will say a little bit about entanglement entropy, which is a measure for how much entanglement we have. And I'll do that both in the quantum mechanics and the quantum field theory setting, just to give a bit more of an overview of this. And then I'll turn to separable states, so states which are not entangled, and I'll explain why those should be interesting and what we can do with them, trying to construct some of them. And then I'll come to some conclusions and an outlook. Okay, so let me start with the physical motivation of why we should be interested in entanglement, especially in quantum field theory. And I'll take, I guess, a rather broad view here, start with a brief history of entanglement. You probably all know all of this, but I'll briefly go through this anyway. So entanglement is the characteristic trait of quantum mechanics because it tells us where quantum mechanics differs from classical mechanics. And it was first discovered around the 1930s, 1935, by people like Schrödinger and Einstein, probably independently. And one of the early highlights is the 1935 paper by Einstein, Podolsky, Rosen, the EPR paradox, where entanglement is essentially used to argue that quantum mechanics is either incomplete, there should be additional variables describing the system, or quantum mechanics is non-local, so there are correlations between measurement results at space-like separation which do not have prior common causes. So especially for Einstein, the non-local option just was not acceptable. So he strongly argued that quantum mechanics should be incomplete. The next big highlight that I want to mention here is the 1964 paper by Bell, where he derives the Bell inequality, which is satisfied by all realist local hidden variable theories, but which, on the other hand, can sometimes be violated by quantum mechanics. So if this violation also appears in nature, then I guess we have option 2, and together with the EPR paradox, that means the hidden variables seem to be out and nature seems to be non-local. So if you then say, so what does nature say? There is a long list of experiments starting with early attempts in the 1970s and ending, I guess, in the 2000s or even later, where violation of Bell's inequalities has been verified under ever more stringent conditions, eventually leading to a Nobel Prize essentially on this topic in 2022. And the conclusion there is Bell's inequalities are violated, so apparently nature has some non-local effects there. Now, you all know this, but to drive the point home, I'm going to put a footnote here. To keep track of the localization of observables, I guess the nicest thing to do is to use quantum field theories, where everything is relativistic and as advanced as you could possibly get it. And for those kind of theories, there is a 1961 theorem by Ray and Schlieder that strongly indicates, well, perhaps it is a few steps short of mathematically proving, but it strongly indicates that vacuum states of Whiteman QFTs are entangled between all regions of space. And there are actually extensions of this theorem basically saying that entanglement is pretty much everywhere. So it's the rule rather than the exception. So we have to deal in some way with this non-local behavior in nature. So because localization is important, I think the best way to try and investigate this non-local behavior is to use quantum field theories, which take localization into account a bit better than quantum mechanics. So how do we handle this non-locality? So I'm going to mention first the option of Bohmian mechanics, which is perhaps not very popular amongst theoretical physicists, slightly more popular perhaps amongst some mathematical physicists and philosophers of physics. So Bohmian mechanics basically keeps space classical. Essentially, it's a Galilean type of space-time, and then writes down a non-local theory in the space-time, which is a completion of quantum mechanics in the sense that there are hidden variables there, which are particle positions, but not their momenta. So one reason why you might not like that theory is because it is difficult to extend this to a relativistic quantum field theory setting. The option that I would prefer myself, although it's a bit more difficult to actually say something very concrete, I think, is the idea that space-time is emergent anyway. So the space-time is, in some sense, an idealization that we use, which is not fully justified. So a point like localization is not really fundamental, but it's only an effective property that emerges at low energy scales. And if we had a full theory of quantum gravity, we might be able to actually show how this phenomenon emerges in some way. But even without a full theory of quantum gravity, there are some hints that this actually makes sense to take this point of view. For example, in quantum field theories, if you're in a vacuum state, then entanglement entropy, that tells us how much entanglement is there, typically decays with the distance of the regions that you're considering. So that's a hint that says at longer distances, there is somehow less entanglement. So it's harder to get these non-local effects. And at long distances, the idealization of using a space-time might be more reliable. And perhaps another somewhat related point is that there is no communication faster than light. So even if entanglement violates locality in some sense, it's not going so far that you can actually communicate faster than light. Okay, so because I'm interested in the second option, I'm going to see what we can say about entanglement in the context of quantum field theory. And we'll come back to some of these things of entanglement dropping off at long distances. Okay. So let me first say something now about entanglement entropy, first in the context of quantum mechanics, where things are technically a bit easier, and then I'll go and say something about the quantum field theory setting. So in quantum mechanics, I'll immediately take the language of density matrices rather than vectors in a Hilbert space. So we're considering a density matrix on a Hilbert space, which is a tensor product. And then we say our state given by this density matrix is a product state exactly when the density matrix is a tensor product of two density matrices. Or if you like, you can also write this directly in terms of what happens to observables when I have an observable A tensor B, and I take an expectation value, so I trace rho times A tensor B, I get a product of two expectation values. So product states means no measurement correlations whatsoever between regions A and B, or systems A and B. A separable state is what you get when you take a classical mixture of such product states. So there can be classical correlations, but nothing beyond that. And in quantum mechanics, there are also states which are not of that form, and those are the entangled ones. So a state is entangled when it's not separable. Okay, that's the basics on entanglement. Now, some important basic quantities that are always mentioned in the literature: the von Neumann entropy, which is minus the trace of rho log rho. That's always greater than or equal to 0. And another quantity that I want to mention here is the violation of the Bell inequality. So you can measure how much that inequality is violated by taking a supremum over a whole bunch of possible operators in system A and system B. And that gives you a number that lies between 1 and the square root of 2 in quantum mechanics. So these two quantities are important, especially for pure states, because they help you to find out if your state is entangled or not. So if I'm in a pure state, projection on some vector psi, then my state is entangled exactly when the von Neumann entropy is strictly bigger than 0, or when the Bell correlation is strictly bigger than 1. And you can actually find an inequality between these quantities for pure states, where you can estimate the von Neumann entropy from below by something involving the Bell correlation. So that's something I learned from Chialostri and Carpi, but as far as I know, is not yet published. So this von Neumann entropy and this Bell correlation quantity are perhaps early forms of an entanglement measure. They tell you whether a state is entangled or not, and they also put a number on it, but they're not very good if you go to mixed states. So in a slightly more general setting, what we want is a kind of distance, and I'm putting that in quotes because mathematically it's not really a distance, from a state to the set of separable states. And the von Neumann entropy and the Bell correlation are not very good for that, because the von Neumann entropy is also positive, strictly positive, when I have mixed separable states, so only classical correlations, but still von Neumann entropy is strictly positive. And the Bell correlation can be 1 even for entangled states, if I allow mixed entangled states. So one of these is somehow not specific enough, and the other one not sensitive enough to really be a reliable measure for entanglement. So what I want to consider instead is the so-called entanglement entropy, which is a good measure for entanglement. And I'll take the infimum of relative entropies between my given state rho and any rho prime that gives a separable state. And in the case of quantum mechanics, there is a formula you can write down for this relative entropy, which is rho log rho minus rho log rho prime. And that gives you a non-negative number. So important to note, perhaps, is that this relative entropy is not symmetric in the two states. So for this reason, also, the thing we're looking at is not really a distance from one state to another state, because it's not symmetric. But it does have a reasonably good interpretation. It's the expected amount of information that you gain when you thought that the state of your system was rho prime, and you then learn that it is actually rho. So if I take the infimum of a separable rho prime, I'm basically saying I want to know how much information I expect to gain when I thought my state was separable, and I then find out it isn't. So that's a reasonable entanglement entropy measure, at least in principle. It's not so easy to compute this, unfortunately. So moving on to the quantum field theory setting, the kind of situation that I have in mind is we take some spacetime with a Cauchy surface sigma. I take two open bounded disjoint regions A and B in the Cauchy surface, and then their domains of dependence in the spacetime. To each of those regions, I can associate an algebra. So there's an algebra for A, there's an algebra for B, and you can also associate an algebra to the region A united with B. And then there are some basic, well, let's say facts, perhaps you want to call them axioms, about quantum field theory. If my regions A and B in the Cauchy surface have an empty intersection, so they are space-like, then the algebras should commute. If the closures of the regions are still have still an empty intersection, so the regions don't even touch at the boundary, then typically we have the split property that allows us, if we look at the Hilbert space representation of this theory, to write the Hilbert space as a tensor product of two copies of the Hilbert space, where algebra of the region A acts on one factor and the algebra of the region B acts on the other factor. So here we get the tensor product in that we normally use to describe entanglement. If my regions A and B together do not form my entire Cauchy surface, then essentially any reasonable state on the entire space-time, the entire Cauchy surface, is going to restrict to A together with B as a mixed state. So there's essentially no chance of talking about pure states in this setting. We need mixed states. And then if you want to talk about relative entropies, you have to deal with the fact that the algebras we have here are typically not just matrix algebras, but they're algebras of a different type. But you can use Tomita-Takasaki modular theory to actually formulate relative entropies and then define the entanglement entropy using that. So that's a topic that I won't be saying too much about here, but I just want to mention that everything can be done rigorously there. Okay, so what happens then with entanglement entropy in quantum field theory? So this is a brief summary of some results out in the literature. Some of those, especially in this language, are also in the little book of Stephen Hollins and myself. So here I'm considering a static space-time. I fixed one region A in the Cauchy surface, and I moved the other region B further away, where I have a distance r. I assume my theory has a positive mass in there, and then for the ground state of my theory, I can show that the entanglement entropy actually drops off exponentially. So it really gets small at large distances, and that holds for a number of cases where this could be verified. So free minimally coupled scalar fields, free Majorana fields, but also some interacting quantum fields in 1+1 dimensional Minkowski space. This could be verified. So typically, if you have a mass 0 in your theory, you might expect a somewhat slower decay, perhaps polynomially rather than exponentially. But as far as I'm aware, this idea that entanglement entropy falls off at larger distances does work in all examples that I know of. So this is some indications that fit with the motivation that I gave, that at long distances entanglement is somehow small, and the approximation of using a spacetime is a good approximation. Now, from this point, I want to move to the separable states. And you can already see one reason why we should be interested in separable states, because the entanglement entropy is defined by comparing any state to essentially the nearest separable state. So the more we know about separable states, the better we might be able to try and compute or at least estimate entanglement entropies. Okay. So for the separable states, I'm going to use a toy model just to keep things a bit simpler. And the toy model is the free scalar quantum field theory. I will allow, in principle, any globally hyperbolic space-time. And it's basically known how to define free fields on any globally hyperbolic space-time. And it's known how to find a good class of physically reasonable states. Those are called Hadamard states. So for the purposes of this talk, I'll focus on quasi-free states, which are fully determined by a two-point distribution. So all we need to talk about is two-point distributions, and we don't need to go beyond that. And you can think of those as just an expectation value of two smeared quantum field operators that I'm smearing with some test functions f and g there. Okay, so what do I need for my two-point distribution to be a good two-point distribution? I need basically three properties really to be a two-point distribution, and the fourth one is to be a nice two-point distribution. So what I need is certainly something of positive type. I need to be able to define an inner product to get a Hilbert space. So that's the first property there. I want to satisfy my equation of motion, which is a linear equation here. So my two-point distribution should satisfy this equation in each of its 2 points. The anti-symmetric part of the two-point distribution is fixed by the canonical commutation relations. So I'm writing here some distribution E of x and y. That's basically a scalar distribution. That is essentially fixed by the geometry of the spacetime and the equation of motion that you choose. But I'm not going to specify in much detail how to get it or what it is, because I don't need it that much. And the last condition that I write there is that the wavefront set of my two-point distribution should be contained in a certain fixed set. That is the Hadamard condition. So the wavefront set tells me where the singularities of my two-point distribution are. So this is a restriction on how singular my two-point distribution can be. Perhaps the most important consequence of this condition is that any two-point distributions differ by a smooth function. So the singularities in two-point distributions cancel out if I subtract them. And that's a nice fact. So these Hadamard states have been important also in formulating perturbatively interacting quantum field theories. They are nice because they have finite energy densities everywhere. So they are known good class of states. Okay. Now I want to talk about separable states and perhaps even more specifically product states. And product states are pretty easy to characterize if you're thinking especially of quasi-free states. So in this equality there, I'm looking at while operators where I take complex exponentials of my field operators. And you can recognize a product state basically by looking at the two-point distribution. If there are no correlations between the two regions that you're interested in, so the domain of dependence of A and the domain of dependence of B, if your two-point distribution vanishes there, then you have a product state between the algebras of those regions. Okay, so that's what I'll be looking for, two-point distributions that vanish on sets of that form. Now, to find such two-point distributions, I need to basically satisfy all of those four conditions that I have. And it's actually nicer to go to an initial data formulation where the equations of motion is already built in. So that essentially solves one of my conditions that I had there and leaves me with the other ones. So I'll write in the initial data for a two-point distribution as a 2x2 matrix. And I'll put some indices ij going from 0 to 1 there, where you can think of I and j as the number of normal derivatives or time derivatives that I take in one of the two slots of my two-point distribution. So given any two-point distribution, any Hadamard two-point distribution, we can find other ones basically by adding something, a term W2, which is smooth function of two variables, which should be symmetric in the two arguments because I don't want to change my canonical commutation relations. It should be a solution to the equation of motion in each of the two variables. And then positivity is always the nasty condition. So W2 smeared with test function f bar and test function f should be greater than or equal to minus omega 2 with those same test functions put in. In general, that is a difficult condition to verify unless you say, I'm going to make my life easy and I'm going to assume that my W2 itself is already of positive type. That's an easy way to find a lot of other Hadamard two-point distributions. You might not find all of them, but you will find a lot of them. So the strategy that I'm going to follow is to take any Hadamard two-point distribution and then say, I want to add something like this W2 of positive type in such a way that it cuts away the correlations that I don't want, and then I end up with a separable state. Okay, so here's a somewhat simplistic construction, perhaps. I take any Hadamard two-point distribution. I take two bounded open regions in the Cauchy surface, and I'm going to assume that the closures of those regions don't intersect, so they're really separated by some non-zero distance. And I then want to remove correlations between the domains of dependence of those regions. How do I do that? I choose some cutoff functions for the regions A and B. So some nice test functions in my Cauchy surface, which are identically one on the region A, respectively B, but such that the supports of those two cutoff functions have an empty intersection. And then what I want to do is define from my initial data of the original state another 2x2 matrix of smooth functions, just saying I take the initial data of my state, I multiply it with a cutoff function a in the variable x, cutoff function of b in the variable y. I put a minus sign in front of that, and that gives me something smooth. The fact that this is smooth has to do with the Hadamard condition on the two-point distribution omega. The singularities of the initial data of this two-point distribution are all on the diagonal. And when I use these cutoff functions, I never get close to the diagonal. So whatever is left is actually nice and smooth. Now you could say if I would take this V2 matrix as initial data for a bi-solution on the entire spacetime, and I add that to my two-point distribution, then I will have cut out all the correlations between the regions domain of dependence of A and the domain of dependence of B. But what you get is something strange, because it's not this V2 is actually not even a nice symmetric thing. Now, you can symmetrize it and then try again. But even that doesn't work, because what we add here is not of positive type. And it might actually destroy the positive type of the two-point distribution that I started with. So this is not guaranteed to give me a state, because I have not shown yet that what I get is of positive type. Okay. So at the bottom here, I give a brief proof to show that the V2 thing itself is not necessarily of positive type. You can just choose test functions in regions A or B, play around with the sign until you get something negative. So if we want to take a state, add something of positive type that cuts away the correlations, then we will need to do something more than what I've done here. Here I've cut out the correlations, but I need to restore the positive type. Okay. So how can we do that? Well, we can think of this V2, this 2x2 matrix, as an integral kernel of a compact operator on an L2 Hilbert space, where I'm looking at an L2 space with two components, and then write this operator as L. There is a polar decomposition for this thing. And then in terms of that, I can define another operator L tilde as L plus L star plus the modulus of L plus the modulus of L star. So what's happening here is that L basically cuts out some of the correlations I don't want between region A and B. L star then cuts out correlations between B and A swapped. And I add the modulus of L and modulus of L star in order to get something of positive type. And then we will need to do a bit of work, not too much actually, to show that this L tilde itself actually has a smooth integral kernel. So its integral kernel is given by some 2x2 matrix that I'm calling here V tilde. And this V tilde is then something that I could use as initial data for the extra term W2 that I would like to add to my given Hadamard state in order to define a new one that is a product state between the regions domain of dependence of A and of B. So with a bit of work, we can actually take any quasi-free Hadamard state on any globally hyperbolic spacetime, some nice regions A and B in the Cauchy surface, cut out the correlations, add a bit more to restore positivity, and then construct a state that is still quasi-free Hadamard and a product state between the given two regions. These kind of states might be interesting for trying to estimate the entanglement entropy between the given state and the new state. That's something that I haven't done yet, but I would like to do that at some point in the near future. Now, there is another topic I wanted to talk about that makes all of this a little bit more challenging. So here I'm going to go to 3+1 dimensional Minkowski space and ask the question, can I find separable states that have some symmetries, like Minkowski space symmetries, translation symmetries, for example, in space and time. So for this purpose, for simplicity, I guess I'm going to assume that the mass is strictly positive, although I think the argument should also work in a massless case, but I haven't fully checked. So the result that we can get with some work is if I pick any positive number r, I can find a quasi-free Hadamard state, which is stationary and homogeneous and isotropic. So it's basically invariant under all the symmetries of Minkowski space except boosts, has essentially the same symmetries as, for example, thermal states. And I can get the two-point distribution in such a way that it is zero when I take 2 points, which, let me simplify this. If I take 2 points at the same time, when the 2 points are of a distance capital R away from each other, at least. So at a fixed time, this cuts out all correlations above this fixed distance R. On top of that, I can estimate the energy density of this state. So the energy density is constant throughout space-time, and I can put an upper bound on this. This upper bound might not be sharp, but as far as I know, this is the first upper bound for this type of state in existence. So I'm glad that we have anything here. Well, perhaps I should say at this point, in a much earlier version of a similar talk, I had a bound that was actually much, much, much worse than this, with a 10 to the 10 to the 10 or something in it. So 10 to the 31 is already a lot better than that, although I would like it to be a bit better still if I could. Okay, so this property 1 here shows that we get a product state between any two regions that are space-like separated by a distance at least r. The energy density cannot be arbitrarily small. I could also give you a lower bound for this, but that's essentially, let's say, of the order 1 rather than a 10 to the 31. So there's a lot of space between the lower bound and the upper bound of the energy density that I know. The upper bound is not sharp, but at least it has the nice property of falling off exponentially in the distance, which is also something that I like, and that seems to be in line with the fact that entanglement over large distances seems to cost more energy or is harder to use than over short distances. Okay, so let me say a little bit about how to do this. The basic idea of the construction is very similar. So now I'm going to start with a two-point distribution that's already translation invariant, namely the Minkowski vacuum. I want to construct another two-point distribution that's translation invariant by adding a smooth translation invariant function W. So here W essentially only depends on the difference variable. It should be a smooth, real solution to my equation of motion. It should be of positive type. Positive type basically means in this setting, because it's translation invariant, that the Fourier transform should be greater than or equal to 0. And it should be an even function, because I don't want to change the canonical commutation relations. So going to initial values, that means that the normal derivative of W is 0 anyway. So I just need to look at the initial values. That's nice. And I need initial values that have Fourier transform that's greater than or equal to 0 to get something of positive type. I need the initial values to basically remove the initial data of the initial values of my vacuum two-point distribution. If my point x is, excuse me, I have a mistake in this second item there. If the norm of x is greater than or equal to r rather than 0, otherwise there would not be any correlations whatsoever, and that's a bit more than what I can prove. And then on top of that, I want to estimate the energy density. So what I do here is renormalize things by subtracting the vacuum energy density. And then I've got this expression there. So minus the Laplacian plus m squared of my function w0 at the point 0. That is something that I would like to be small. So now we're looking for such a function w that does all of this. One thing you could try, very similar to what we did in the other more simple construction, is to say, let's take a test function, let's cut out the correlations we don't like. So for some cutoff function chi, which is identically 1 near 0, we could take w of the form given here. So when I'm a bit further away from 0, I actually remove all the correlations in my two-point distribution, and only near 0, my function w vanishes. So once again, that removes correlations, but it destroys the positive type. To get something of positive type, what I could do is take this expression and then add something of sufficiently small support, so I don't introduce new correlations, and something that is of positive type, and in some sense that is positive type enough to counterbalance anything in this expression that might be negative type. So what we need to investigate at this point is test functions of positive type and then lower bounds of their Fourier transforms. And that's what we need to finish this construction. So let me say a bit about test functions of positive type. So I fix some L bigger than 0, and I'm looking at the one-dimensional case here. I have some epsilon that tells me something about how fast my Fourier transform falls off. And then I'm first going to cite an old theorem, which is about upper bounds of Fourier transforms. And this is basically well-known classical stuff. So we know that the upper bound of a Fourier transform can't fall off exponentially, because then the test function would be analytic, and then it has to be identically 0. But there is an old theorem by Ingham that says we can get test functions of essentially arbitrarily small support in the interval from minus L to L, with a Fourier transform that is bounded from above by e to the minus norm of k epsilon norm of k for all k, if and only if my epsilon is a decreasing function for which the integral from 1 to infinity of epsilon of k is finite. So that is an if and only if result that essentially characterizes exactly how fast test functions can fall off. Now, that's upper bounds. For lower bounds, I didn't find much in the literature at all. So I had to do some proofs myself. So to complete the construction, I wanted lower bounds, and I came up with the following result in a similar spirit. Suppose in addition to this L and this epsilon, I pick a number gamma between 0 and 1. I assume that this integral from 1 to infinity of epsilon k over k is finite as an Ingham's theorem. And on top of that, I assume that the lim inf of k to the gamma epsilon k is strictly positive. Then there exists a test function supported in the interval from minus L to L, which can be arbitrarily small, such that the integral of g is 1, so it's normalized, and the Fourier transform is bounded from below by the same kind of exponential that appears in Ingham's theorem. So we need, in this theorem, a slightly stronger assumption on epsilon, this extra assumption about lim inf, with this parameter gamma in there, in order to get the same type of lower bound. Unfortunately, this result is not in both directions. This is just an if-then, so it might not be fully sharp, but unfortunately, I was not clever enough, or I did not see how to get an if and only if result in this case, and it was actually good enough for the purposes that I needed it for. So to prove this result, I'm just going to say a few words about the technicalities that go into this. What we do basically is the same strategy in a sense that Ingham uses, is to construct test functions by using repeated convolutions. So there is a standard construction of test functions in an interval from 0 to a that basically says we take characteristic functions of an interval from 0 to a1, and then we normalize that by dividing by a1. We take a convolution by something similar with a parameter a2 and then an a3, etc., etc. If my a's are a decreasing sequence that have a finite sum, then we get a test function. And basically the support lies within 0 to a if this infinite series adds up to something at most a. So that's a construction of test functions, which actually gives you a lot of control also over the L1 norms and L infinity norms of the elements in the sequence of for which I'm taking a limit here. And you can estimate all of this basically in terms of the numbers A1, A2, A3, etc. that go into the construction. So what it doesn't do is give you something of positive type. So what I did is basically replace this basic building block function, this characteristic function, by something else that is of positive type. So I'm going to call that eta here, the parameter an there. So to see that this is of positive type, what you can do is first look at the thing in brackets there, where I have a characteristic function over a symmetric interval. So that's a real even function. The Fourier transform is real and even. When I take the convolution of that thing with itself, the Fourier transform is going to take the form of a square. So that's already greater than or equal to 0. That's a good start. That's of positive type. But it might not be good enough to actually control lower bounds, because greater than or equal to 0 in this case means that it's going to periodically also be 0, and that you can't control the lower bounds. So I take the square of this thing in the x variable, which means that on the Fourier transform side, I'm going to take this non-negative thing convoluted with itself. And then you can actually show that that is going to give you something strictly positive. And with a bit of work, you can actually compute this Fourier transform of this function and find pretty good upper and lower bounds that you can actually work with to do some estimates. So the other parameters of 1 over an coming in there and the 3 over 2, that's just to get a good normalization of this function. So I'm going to use that as a basic building block in my construction, and then I can construct test functions G basically by using the same type of repeated convolutions. And I can estimate the support of G and the L1 norms and the L infinity norms of any of the terms in my series there. And I can estimate all of that in terms of the AN that go into my construction. So that allows me to construct test functions of positive type for which I can control upper and lower bounds pretty well. And then all I need to do is to find suitable AN to make sure that the support can be as small as I like and that the lower bound is still what I want it to be. Okay, so an example. There are a class of functions that are sometimes useful in mathematics called Gevrey class functions that fall off almost exponentially in some sense. So any test function of that class can be dominated by a test function of positive type with arbitrarily small support near 0. That is one of the consequences of this theorem that I showed you on the previous slide. So that's a useful thing perhaps to have in suitable constructions if you want to construct something of positive type. So at this point, another note to make is that the only prior result that I know of that did something with lower bounds of Fourier transforms of test functions was only an asymptotic result. That was by Fuster and Ford from 2015. So the result of Fuster and Ford might also be used in my construction, but well, it gives you separable states, but it gives you no way of estimating the energy density from above. So it just wasn't sharp enough for what I actually wanted to do. Okay, so let me come now to some conclusions and an outlook. So I hope that I convinced you, if you didn't believe this already, that entanglement shows that nature is, at least in some sense, non-local, and that it's interesting to use quantum field theories to investigate the dependence of entanglement on space-time localization. Entanglement entropy in vacuum falls off with the distance. So that's a nice thing that is in line with the idea that space-time is emergent. And it compares a given state to the nearest separable state, which brings us to the question, what do we know about separable states other than that they exist? I hope to have convinced you that nice separable states exist, at least for free scalar quantum field theories, where I constructed them pretty explicitly, I hope. So we can get them as small perturbations of any given quasi-free Hadamard state. And that should be separable between two given bounded regions, as long as the regions don't touch. And in Minkowski space, we can do a bit more. We can even get translation invariant states, also rotation invariant, if you like, and they can be separable over any over regions that are separated by any prescribed distance r. So if you like, you could take here for r the Planck length and get a perfectly valid Hadamard state of a quantum field theory that has no correlations whatsoever beyond the Planck length. So it looks as classical as you could possibly get it. The only price to pay there is that this state will have a constant energy density that might be rather large. So I have an energy bound that falls off with distance, and it's very nice in that regard, but the numbers involved there might still be a bit larger than what they need to be. The bound might not be sharp, but at least the exponential fall-off is once again in line with the idea that space-time is emergent, that at long distances it's a good approximation, etc. Okay, so I put here on this slide also the note that creating or maintaining separability apparently costs energy, but of course creating entanglement doesn't cost any energy. That's just decoherence that comes for free always. Okay, some open questions here. One is, can we obtain or sharpen the upper bounds that I had on the energy or energy density of separable states? That is a work that's still in progress. I would like to understand better what's happening there. Can we use nice separable states to estimate entanglement entropy? So we're assuming that our given state is close to some nice separable state rather than just any separable state, and we compute the relative entropy. The question then also is, are the bounds that we get in that way much worse than existing bounds that are general separable states? And as a comment here, I think with the basic constructions that I've done, extensions to other free fields and principles should be straightforward. So that should also be possible without too much trouble. Okay, thank you very much for your attention.
So thank you very much for this nice talk. We have a lot of time for questions, so please just unmute yourself and ask. Well, I cannot hear any questions, so maybe let me ask, was it all going on Minkowski, or does it apply to a larger class of spacetimes?
The construction of the separable states, the first result that I showed basically is in any globally hyperbolic spacetime, but for translation invariant states, of course, we're in Minkowski space. For the entanglement entropy results, there we were looking at vacuum states. So some of the results there, especially for free fields, also apply to static spacetimes where you have a good definition of what a vacuum state is. Results on the integrable quantum field theories that we had there, that's only in 1+1 dimensional Minkowski space, because I wouldn't know how to formulate those integrable models in a precise way in a curved spacetime setting.
Okay. So I can see some question from Albert in a chat. Let me read. Can I ask about the difference between the types of entanglement entropy laws? Since there are area laws and volume laws for entanglement entropy, why is there such a difference?
Could you repeat that question?
Can I ask about the difference between the types of entanglement entropy laws? Since there are area laws and volume laws for entanglement entropy, why is there such a difference?
So the area laws presumably refer to a situation where we have two regions that make up, well, essentially all of a Cauchy surface, and they have a boundary between them, and there the entanglement in some sense scales with the area of that boundary. Of course, in the setting that I described here, that also allows curved spacetime situations. What you would typically do is keep your two regions apart a little bit so that they don't touch, and then consider a limit where the distance goes to zero. And then the other was volume laws.
Since there are area laws and volume laws for entanglement entropy, why is there such a difference?
Yeah, I'm not entirely sure what to answer there.
Okay, but I have the impression that the person who asked the question is already happy because he wrote yes beneath. So I think it's answered. So
Yes.
any other questions or remarks?
Excuse me, can you hear me?
Yes?
Yes, I can hear you.
Yeah, I may have a question. So, is there any specific reason why you are studying free scalar fields or free fields in general? So you're not considering interaction so far.
Right. Well, so for the earlier section on entanglement entropy, we had some results on interacting quantum field theories there. For the separable states, I started with free scalar fields because that is something that we can describe fairly easily, also in a curved spacetime setting, and where we can get some easy results. If we're talking about interacting quantum field theories and we want to go to curved spacetimes as well, then I guess things typically get a lot harder, and it's not immediately obvious what would be the nice class of states that we should consider in analogy to Hadamard states for free fields. And I guess the techniques that are available to actually construct something are perhaps not quite good enough yet to actually do something there. It's not that I'm not interested in interacting field theories. It's just harder to do something, especially if you want to keep a curved spacetime background possibility.
Well, I see. Thank you.
You're welcome.
Can
Any
I
other
ask
questions?
can I ask a very elementary question? So I was not familiar with this entanglement entropy that you defined. And does this entanglement entropy become simpler if you restrict if we only consider pure state? Does it become something easier to compute, or? Or is it related to the usual entanglement entropy for pure state, which is just the fundamental entropy for the reduced density matrix?
Yes. I think it reduces to that
Oh,
if you
okay.
take pure states.
Okay, but
Yes.
that's not quite evident.
it takes a bit of work. So if
Okay.
you take this very general definition of entanglement entropy using modular theory, and then you put in a pure state, then I think it essentially reduces to the quantum mechanical formula that you get there.
Okay. I also have a question about the earlier part of your talk, where you mentioned that entanglement in vacuum falls off if you go far away. So to prove this, so you had to control this entanglement entropy defined as an infimum for all separable state world prime. Is it correct? So
yes,
yes.
yes.
In that case, did you have to sort of explicitly construct this rho prime and compare? And it looks like a very formidably difficult computation to do.
Yes, so we certainly didn't find the infimum, let's say it that way. We basically, so in the work with Hollands, we basically did some construction that gives us some good guess for what
a kind of
variational
estimate.
Yes. But a point I would like to make here is that in the work with Hollands, we found some separable state, but that might not have been a very nice one. In particular near the boundary, I have no idea if whether that state would have, a finite energy density or things like that. So it is some separable state that allows us to give an upper bound on the entanglement entropy, and that was the result essentially.
Okay, all right. So that's motivated your study of constructing good separable states. Okay.
Yes, I basically want to control the separable states in order to have more options of perhaps trying a different separable state and maybe getting a better estimate on entanglement entropy.
Okay, thank you. Yeah.
Okay, any other questions or remarks?
If nobody asks, I'm curious about what you said in the beginning about the relation between the idea that the space-time is emergent and all these entanglement stuff. So I didn't see the connection very clearly.
Well, I guess the connection is a little bit vague. So the idea is that if you take the fundamental point of view that space-time is an approximation that we make that's not really justified, so we should come up with a theory that's somehow formulated differently, some quantum gravity theory formulated in a different way, and then in a suitable regime, in a suitable limit, basically the space-time thing comes out. That is basically one way to handle the fact that quantum physics gives you non-local behavior in nature. Basically to say, well, non-local, what does that mean? This localization shouldn't be there in the first place. Now, of course, on long distances that we typically work on, the approximation that we make of using a space-time is a very good approximation. We use it very effectively in very, very many situations. So that makes you wonder whether the theories that we have actually are consistent with the idea that at least at long distances, having a space-time is a good approximation. And the fact that entanglement entropy, for example, falls off very fast at large distances seems to show that this non-local behavior is difficult to reproduce at large distances. So especially at large distances, it's a good idea to use a space-time manifold in the background. And maybe at very short distances, it might be very easy to get all kinds of non-local behavior, and you would see very clearly that the use of a space-time is a bad idea and we need to do something else. So it's perhaps mathematically not very cleanly and precisely formulated, but there is a rough intuition behind there that what we can do is consistent.
So are you trying to start from a local theory, which is a fundamental theory, or that's...
Well, that's a difficult question. If you're
Yeah.
if you want to take the point of view that space-time is emergent, so it's not a fundamental thing, then the question is, what should a local theory be if you want it to be fundamental? So the word locality is perhaps not available at the most fundamental level.
Of course. So locality in the higher sense, but
yes, yeah.
But anyway, I mean, if we try hard, we can maintain entanglement for long distance. So that you can never avoid by doing anything.
Right? That's true, but you have to try hard. You have to put in a lot of energy.
Yes.
I mean, in quantum mechanics, this is somewhat different, of course, because you can just take, ground state of system A, tensor ground state of system B, and that's the ground state of your whole system, and that doesn't care about the distance, and it's not entangled. In quantum field theory, that's a little bit different. So that also makes me wonder about, in quantum field theory, are there fundamental limits about how much energy it takes to maintain a certain amount of entanglement or separability over certain distances? So the balance between energy and entanglement is, I think, an interesting topic.
Thank you.
Okay, if there are no further questions, then maybe we can thank Ko again and stop the recording, and then there will be an opportunity to ask more informal questions.